code written by the clinically insane is what I would call this, and to be frank, a lot of other OOP style code I've seen written in C. But OOP is useful for a lot of problem classes, and it is often the case that we wish we had OOP style in C. So what I want to do is give you guys the complete spectrum of, okay, this OOP practice is useful and improves the structure of your program, all the way to this is clinically insane, why do you not just use C++ at this point? And the project we're going to use to demo this I think is actually pretty cool. You can see I've got two like terminal Tamagotchi characters here. These are actually Sanrio characters, but it's a Tamagotchi style game. And these of course inherit from a base class of a Tamagotchi character. And we're going to see exactly how we do that. And you can see here I can feed them different kinds of food. And so the food is also part of the OOP magic. And this is all written in C. Now imagine I asked you in a coding interview how you would model these OOP concepts in C. Think about it for literally 2 seconds. Classes and objects is an absolutely easy, obvious one. You can literally model them as structs, okay? Or like you do a typedef struct, right? It is that simple. And your methods of your class will simply become functions that take in a struct pointer as the first argument. It is that easy. Now think about what we're going to have to model for a Tamagotchi game, and that becomes the members of our class, which is really just a struct typedef. Now we've got everything that a Tamagotchi object would ever want, for example, the current action that it's performing, the emotion that it's experiencing, how much hunger it's in, its stomach capacity, and we can see these values being modeled in the demo with a little bit of divergent behavior from our subclasses. So over here on the left, Kuromi does not like hamburgers because they have pickles on them. So if I feed Kuromi a hamburger, it will get mad at me, but it loves pizza, so if I feed it pizza, it will become happy again. Now over here on the right, we have Butts, who does not like pizza, but does like hamburgers. So if I feed it pizza, it'll get mad at me. If I feed it hamburger, it will get happy. And modeling this divergent behavior in C is absolutely possible, even though these both inherit from the high-level Tamagotchi type. Have a look at these 3 struct definitions right here. You'll notice something really important pretty quick, which is that the Super Tamagotchi class is the first struct member of our 2 subclasses. So we could go and put other stuff in here like bool, int, whatever, it doesn't matter. The important thing is that the super class that we're inheriting from is the first member. The reason for that is simply that this member will share a memory address with the instantiation of this struct, which means that when we do method calls, we can just cast the struct that we've allocated directly to the base superclass and it'll just work. I fully appreciate that was a lot of words, so let's take a step back, relax, and I'm going to prove that point to you. Now what you'll notice I have here is an instantiation of the Kuromi class, which has as its first member the Tamagotchi superclass. So if I were to print out the memory address of that instantiation of the Kuromi class, you'll notice that it will be exactly the same as if I were to print out the memory address of the .super member. And this is the result of that print right here. And this is a very important result. So you can see here for the high level Tamagotchi class, I have a constructor here called tinit, which basically just goes ahead and sets a whole bunch of defaults. Now, for example, if we want custom ASCII art per character, that's where our subclasses are going to have their own init functions as well. And you can see here, I have a binit function. Now, the result that we just saw before, where they share the same memory address, is important because what it allows us to do is take a subclass and directly cast it to the parent class and just call the method directly on it. And that is a way that you could model method inheritance on your subclasses. So, struct definitions and instantiations for classes and objects. I'm going to mark this as green. I like this. This is good. I think if I see this in a code base, that is a fair way to model an object-oriented problem. And as just mentioned, for inheritance, we can make the superstruct the first member of the child struct, which gives us both method inheritance and member inheritance because we can access the superstruct's members as well. This I fully support. I think this is a good way to do things in C. If I see that, I like it. Getters and setters, oh my god, I hate these so much, even when I'm programming in real OOP languages, okay? I just think they add so much unnecessary fluff for what should just be a very simple operation. I just hate them, and I am so glad that they are usually like not the case in C. So if I see this in a code base, I'm just like, oh my god, I hate it, I hate it. Just give me the struct, let me access the struct members as I want. C is all about being able to do what I want, right? So just let me read the struct directly, please. The only situation where I think these are defensible is if you're making a super complex library like a graphics or physics engine, and you have super complicated objects and classes where you don't want the members to be accessible by the people using the library. In that case, you use something called an opaque pointer, which is where you just export a type def, you do not export the type information of the struct. In that case, sure, you can do getters and setters for a component of the API, but honestly, if you're just doing like a simple program that doesn't have all of that and doesn't need that, if I see this, and I have seen that, I have seen this pattern in relatively simple code bases, please do not, it will drive me insane. Now we're going to cover polymorphism, which is the ability for subclasses to exhibit different behaviors. To demo polymorphism to you guys, we're going to look at both the food items that we can feed the character and how the different characters react to the food items. So for example, if I feed pizza, you'll notice we have a limited number of slices. So if I keep feeding it until we hit 0, you'll notice that the stomach value does not change because we've ran out of slices. The hamburger is eaten one layer at a time, so you've got pickles, lettuce, tomato, and the patty. So if we feed it, you can see our layers go down until it's just the patty, and then we can't feed it anymore. Now, all of these food items are derived from the same food class, but their eat consumption methods work in very different ways, so let's dive into it. You'll see a very familiar pattern. We have a high level food definition and then a couple of subclasses, and you'll see we have a type of food, so that's just simply an enum that tells it what kind of food it is. And we have the value, so that's how much stomach capacity that will give to the Tamagotchi when it gets fed. You'll see we've got pizza, which has the additional member of slices, and we've got the hamburger, which has the additional members of pickles, tomato, and lettuce, which basically say like, if it's true, then we can eat it. If it's false, then it's eaten already. Here we are in the demo code, which is where we actually go ahead and feed the Tamagotchi based on the user's input. Now, what you'll notice is something very interesting. No matter what item we decide to feed the Tamagotchi, we are calling the same tfeed function. How can that be the case? And you'll notice even more interestingly, there's no cast on this. So we're not using the same memory address cast trick as earlier, because of course, it has to change its behavior, like the pizza has to decrement the slices, the burger has to toggle the pickles and the tomato and the lettuce, so we can't necessarily use the same trick as before because it's not inheritance, we're trying to get polymorphism here. And for this, C11 generics are our friend. So keep in mind these were introduced in C11, so if you want to use this functionality, you need to compile to the C11 standard. However, it is really cool because what this gives you is compile time dispatch based on the type of the argument. So for example, in this macro here, so keep in mind, this is a macro, not a function. We are essentially doing a generic, you can think of it as a switch statement on the type, and we can say based on the type of the pointer that's passed into this tfeed macro, we can call different functions based on that type. Isn't that really cool? So for example, pizza and hamburger both have custom behavior. So they're going to go to their individual custom methods. However, the default, so if we define a new one, so for example, celery was another one we had, that will just go to a default that you can see here uses the base class, which again is going to use that pointer cast method we talked about just before. And here we can see that in action. So this is tfeed pizza, which gets the full type information of the pizza class. And so we can do things like check the number of slices and simply do nothing if the slices are equal to 0. You can see we can decrement the number of slices at the end. We can feed the character normally. We can calculate the remaining total food value based on how much has been lost so far. Like we can do all kinds of custom logic in here that we like because we have full access to this type. Yet, the API still remains the same, and that's because we have that whole generic dispatch thing here where we can offload that to something that knows what the real type is. So for polymorphism, I'm marking generics as something that I really like. Let's use it. It's in the C standard, we have it for a reason, it's cool, it's nice, let's do it. Generics are cool and they can help us out with one layer of polymorphism, but what if we need two? So for example, I mentioned to you before that the Tamagotchis have different reactions to different kinds of food. So for example, pizza still needs to act in its own custom way where it decrements the slices and everything, but it has to react differently to different Tamagotchis. One really likes pizza and one hates pizza. So how are we going to model that? Well, doing it with generics then becomes really tricky because you essentially have to build out a big generic, like a big generics tree that kind of expands for however many different behaviors you want to have. So there's surely got to be a better way to do this. And that's what this void pointer here can help us out with, where we essentially allow the Tamagotchi to specify a custom eat function based on which subclass it is. That subclass can then check the type of the food that it's eating and decide to take action based on that. There's actually a lot of concepts bundled into that one explanation, so let's take a step back and I'll explain what this actually means. You'll notice that in the base Tamagotchi food class, we have a member that specifies what type the subclass is going to be, and that's just an enum that we've defined up here. So when we do things like T-pizza init or T-hamburger init, they can set that type directly, and then we can then access that as part of the base superclass. This is a form of runtime type information that our subclasses and their methods can use to directly change their behavior based on the type information. Now I'm going to give a warning about using this technique because this is where things become a little bit messy, so please use this method as sparingly as you can. But you can see here what we have is a tfood init for the base type, which allows you to pass in what type of food it is. So for example, the tpizza init is going to call this on its superclass and it's going to give it the food pizza type. Similarly, the hamburger is going to do that as well. And it's important to have that type information as part of the base class because you can see that's what this custom eat pointer is going to take in. And the reason we're doing it this way instead of with generics is because now we have to have two layers of polymorphism based on the two different classes. And so if you think about that, if you wanted to build generic macros for it, it would be like combinatorically however many different characters you have and however many different foods you have is how many macros you've got to make. It's going to be a little bit messy. So surely this is a better way. And what we can do over here in the custom eat, so this is Kuromi's eat function, what we can do is check if the type is a hamburger, then we can do a cast and check the pickles. Now again, this is why I said this gets messy, because we have all of this like type checking and the casts involved, and you can easily make mistakes if you're not careful. So you have to make sure that all of your types are done correctly, and there's no cases where you could do an incorrect cast to the wrong type. So this is where this gets a bit messy. It's a decent technique, but please be careful about it. Now what's important is the result of that, because you can see if this is the case, if the burger has pickles on it, then we're going to invert the value and essentially give negative stomach capacity because it really doesn't like them. Now you can see this is a bit more simple for our other character who hates pizza, where we just simply say it's hating the food if the type is equal to pizza, and in that case we'll invert the value as well. Now you can sort of expand this to all kinds of different custom behaviors based on the type and based on the character, and because each character can specify a pointer, and you can see right here in the init function for the characters, they say which eat function they're going to take. So this one has beat, and then this one has keat, k-eat and b-eat. So the two different functions that do two different things, and they're specified as a pointer here. Now what you see as this tfeed base that you see going around everywhere is simply going to operate on the base class, and it's going to do calculations about the stomach capacity based on the value that's passed in. So really it's like not too complicated. You intercept the base feed method, you apply some custom logic around it, and then you just call it again to get the end result. So type information in the base struct. It's useful. I'm going to mark it as orange because it has the ability to get messy very quickly. It's useful, but be careful with how you use it, guys. Now this is okay for when we just have one custom method, but what if we have many? In that case, what we're doing by essentially, if we had more custom methods here, we are essentially blowing out the storage space of this struct because we have to have this many different pointers to functions. So a more common way to formalize this approach is using something called a VTable. Now, a VTable sounds complicated, but literally all it is a struct. I know we got another struct. It's getting kind of out of hand here with all the structs, but please bear with me. That contains all of the function pointers to the custom methods that your subclasses are going to use. So for example, what we can go ahead and do over here is define a K table for Kuromi, which is going to use Keat, and a B table for Bots, which is going to use Beat. And so what this means is that when we do our init functions, we assign the VTable to the correct one for that subclass. And then the calling logic just needs to use that pointer right there. So it's an extra layer of indirection, but what that gives you is the ability to only hold one pointer in your class definition and not have it get too messy, because you can just do everything defined like this. And another benefit of it is that you can have multiple objects that share the exact same VTable. So for example, every instance of this Kuromi will use the same K table that is defined right up here at the top. So there's no duplicated memory, there's no nothing like that, it's all just like in one place. The final one on the menu is VTables for custom menus. Now, I will go ahead and mark this as green, but I'm not going to mark it as a brighter green because, to be honest, I actually do prefer generics for this situation, but VTables can be useful in situations where you need to do that like more than n polymorphism thing. So if I could get away with just like one variant of the behavior, I would use generics, but if I need to do anything more complicated, VTables are okay. Anyway, guys, that wraps up what I think is reasonable to bring into C from other object-oriented languages. Anything past this, I don't want to see it in the code base. I don't want to see you doing funky things. I don't want to see you doing anything more complicated than this, because at that point, just use C++, please. Like, this stuff is simple enough that you can read, understand it super easily. The minute you go beyond this, it's just way too complicated for C. Please just use C++. But these methods are very, very good for modeling certain kinds of problems, so I hope you guys found it useful. If you have any other techniques that you think are good for OOP in C, please let me know in the comments. Thank you so much for watching.